All right, thanks for having me. Um, so let's start with just the Fourier restriction part of this talk. In general, this is a problem that was posed by Stein way back when. So Fourier restriction asks if you have a set, usually some kind of surface with some measure mu, again, like surface measure would be nice there. We want to know when there's a restriction operator that restricts the Fourier transform. So a bounded linear operator from LP of all of RD into just LQ of the surface so that the RF matches up with F hat whenever F hat actually makes sense on the surface. So like if you have a Schwartz function, then F hat is continuous and we can really make sense out of it. Okay, and usually when you look in the literature, they state the theorems more like we're looking for inequalities that look something like this. We're taking F hat and LQ, bounding it by F and LP. And then if we have an inequality like this, we get the existence of this bounded linear operator. Okay, and our surface today will be the moment curve, which is up to these constants t squared up to t to the d. This is the nicest example of a curve in RD you can look at. The affine arc length measure is just dt. So not much you have to worry about with the curvature there. And that turns out to be a good thing in Fourier restriction. The sharp version of this is due to Drury, but a lot of people have worked on Fourier restriction on curves in general. So for the moment curve, this was done in 1985. And the range of P and Q that we're looking at, the best range of P and Q is P between 1 and d squared plus d plus 2 over d squared plus d. And then P prime equals d times d plus 1 over 2q. If P and Q look like this, then we have such an inequality. And I will be talking about this range a lot today. It's called the Drury range, named after Drury. So that's the optimal range for curves in RD. Okay, so if we have this sort of inequality, F hat in LQ bounded by F in LP like this, then we have this bounded linear operator. Okay, that doesn't really tell us much about the pointwise sense of F hat. When F hat is Schwartz, then the restriction operator has to match up with F hat. But when F is not Schwartz, there's this question of, well, can we still ask about the pointwise relationship? And it took a while to actually formulate this question actually in the best way, but Muller-Ritchie-Wright in 2016 proved that on a C2 curve, at least in 2 dimensions, and for P going up to 8 over 7, which is not quite the Drury range, but we'll get there. One pointwise sense that you can talk about is almost every x on the curve with respect to the arc length measure is a Lebesgue point of F hat. And then that regularized value is the same as RF of x. This theorem was improved by Ramos in 2018 to P going up to 4/3. And this is the full Drury range in 2 dimensions. So in 2 dimensions, at least on the unit circle, and you can do similar stuff on more general curves, we have this pointwise relationship fully sorted out. There's also this more general result that I should talk about, that I should mention. Kovac in 2019 proved this really general thing, covers all sorts of sets. Anywhere you have a Fourier restriction theorem, you can get this pointwise estimate, but it does not attain the full Drury range. And in general, I don't think it, I think there is some loss in P. So we use some different techniques, but that is a general result that's pretty cool. Okay, we're looking at the moment curve, d dimensions. So how the results on the previous slide, this Ramos and Muller-Ritchie-Wright worked, is they actually proved maximal restriction theorems. So instead of just F hat restricted to a curve, they looked at a maximal function of this MF hat. And the maximum operators they looked at were, well, a little varied, but the most important one for what I wrote on the previous slide was this M2, which looks like a Hardy-Littlewood maximal operator. But instead of just taking f on the inside, we're looking at f squared. And on the outside, we're raising this whole thing to the power of 1/2. And as it turns out, we also can replace that 2 with r for r between 1 and infinity and ask the same question. The M2 operator is enough to give us the results in the previous slide, but the bigger values of r tell us that these averages, the Lebesgue points, those averages are converging faster. So it's still useful to study r bigger than 2, even though 2 is the minimum we need to get this pointwise sense. And here is my theorem in full glory. There's a lot of text on this slide. First of all, we're looking at dimensions d bigger than or equal to 3. As I mentioned, the case of d equals 2 is pretty well unsorted. The case that Ramos did on the unit circle is basically the same as the moment curve in 2 dimensions. The techniques are all equivalent. So in 2 dimensions, this theorem is due to Ramos. In d bigger than 3 dimensions, we're looking at these maximal functions and these MR. And for R and P and Q in this horrible looking range, we have a maximal restriction theorem. MR f hat in LQ of gamma is bounded by F in LP of RD. Let's look at a picture because parsing that range is not fun. So we have 1 over r on the y-axis here, 1 over p on the x-axis, and I want to first direct your attention to this 1 over r equals 1/2, so r equals 2. You see that 1 over p can go all the way down to the full Drury range. That is, p can go up to d squared plus d plus 2 over d squared plus d. And then as soon as r is bigger than 2, we're actually losing out, and we can't attain the full Drury range. But we can still have some range of p that we get maximal restriction theorems for. And my theorem says that in this region up here, we have those restriction theorems. I also have a counterexample that shows when 1 over r is low and 1 over p is in this range down here, we don't have a bound. The cutoff for the counterexample is essentially r equals p prime. And then there's this unknown region between r equals p prime over d and r equals p prime, where it's unclear what happens. Remember, larger values of r correspond to better convergence. So increasing r from p prime over d to p prime would be pretty nice. But that's currently unknown. The theorem in the simpler case of just r equals 2, that's enough to get us pointwise stuff, looks a little bit nicer. We see the full Drury range here, and we get this corollary. So if f is an LP for this optimal range, then almost every x on the moment curve with respect to arc length measure is a Lebesgue point of f hat. So that's nice. Let's talk about the Drury method a bit. Just usual Fourier restriction. We're looking at f hat, no maximal operators involved on this slide. And we just want to show that f hat in LQ of gamma is bounded by f and LP. Okay, so restriction problems often turn around and look at the extension problem, the adjoint operator to the restriction operator. So the extension operator here is mapping from LQ prime of gamma to LP prime of RD. And it looks like this. And if we can prove bounds of this type, then we get restriction bounds. Okay, and we do this by induction on Q prime, starting with the base case of Q prime equals 1 and P prime equals infinity. And that's some nice, easy Hausdorff-Young. And then the real meat of this proof comes in these next couple, well, this slide and maybe the next one, we'll see. We're going to look at the dth power of the extension operator. And what this looks like there's a lot going on here, but we see this exponential. And this sort of looks like a Fourier transform. Let's define an auxiliary operator, t, mapping on functions. I'll call them capital G. You can think of capital G as like this product of f's. And the way I'm writing it here really looks like a Fourier transform. So we'll use some things we have there to get bounds on t, which gives us bounds on the extension operator raised to the power d, and eventually the extension operator itself. Okay, so we're going to take this Fourier transform, which is supported on the sum of the curves gamma. So we'll decompose the sum of these gammas into offspring curves. The reason that this is called offspring curves is because we started off when we started this induction just with one curve, gamma. And then we raised things to the power d, and we're ending up with all sorts of gamma h's, which are essentially copies of the original curve for h that looks vaguely like this. And these are maybe thought of as the offspring of the original curve, the children of the curve. So with all of these offspring curves, each of them looks just like the original curve. It's an affine transformation of the original curve. So you can apply the induction hypothesis. And there's some notation here hidden. This v of h turns out to be the Vandermonde. That's just some change of variables stuff that's going on. But what we get is that Tg in LP prime is bounded if we look at G integrating first on the inside in T, and then on the outside integrating all of these offspring curves together just in L1, we get this sort of bound. There's a lot of details here that I'm skipping over, but I want to compare this to the maximal case, and I'll just give you the details that are relevant to the maximal case, or the differences between this and the maximal case. What we also get, since we had a Fourier transform, basically, we can use Plancherel, and Tg is bounded in L2, L2 of h, L2 of t, and we have these bounds, we have a linear operator, we can do some interpolation. There's like a page of work to do with the interpolation. You have to work through all sorts of arithmetic and stuff, but eventually you can pull back to a bound on the extension operator. And you get q tilde prime that's a little bit bigger than q prime, and that'll close the induction step. Okay, I said that we're going to use a similar thing for the maximal case, and there'll be some differences. So let's start talking about that. Now we want to do these MR F hat in LQ bounded by F and LP. So what was the first thing that Drury did? It was look at the extension operator. But our MR is nonlinear, so we can't do an adjoint problem. There's currently no adjoint to work with. So we have to linearize this operator. And there's two nonlinearities that I'm seeing here. There's the supremum over S, and there is this power of R and this power of 1 over R. Both of the R's can actually be taken care of by a similar thing. And what we're going to do is obtain an operator that looks more like, well, something linear. So MR eta rho, lots of subscripts here, is going to look like the integral of F hat. Well, essentially F hat convolved with some AX. It's not exactly a convolution, but you can think of it like that. And later on, when we're actually proving things, we will see convolutions with these calligraphic A's. And what you should be thinking there is that whenever you convolve something with one of these A's, it's like we're doing a maximal operator to that function. All right, so let's see how we get this sort of form. We have to take care of the supremum and the power of R. The supremum, we can start by taking rho, mapping RD to R plus measurable. That'll tell us basically for each x an optimal or near optimal S to take. So we're looking at the radius that we want for each x. And if we look at these normalized characteristic functions, then looking at chi rho of x, multiplying in there, will ensure that we're doing an average integral over the ball of radius rho of x centered at x. So as rho ranges over all measurable functions from Rd to R plus, we'll be able to take care of that supremum. Okay, and we can also get rid of the powers of R, but I think I'm going to skip over this part. It's only a 20-minute talk. There's not that much time, but there's details here. And anyway, we end up with eta is essentially any function. There's some restrictions on eta that we'll need, but you can think of it as just pretty arbitrary. And these MRs are f hat, sort of convolved with these a's, but there's this x down here, which is making it a little bit weird. And here's this lemma that says, if we can prove bounds, restriction bounds on every one of these MR eta rows for whichever class of eta and rho we're looking at, then we get bounds on the original nonlinear, the maximal operator that we're looking at. Okay, so we have a linear operator. We can take the adjoint. Let's do it. It looks very similar to the extension operator, where we just have this difference of still having these calligraphic a's. Now it's an a hat in the mix. And that's a little bit weird. It'll make things difficult. But the restriction bound is still equivalent to looking at, this adjoint problem. So we can forge on ahead with Drury and just go for it. We'll do induction on q prime, just like in the classical case. And the base case of q prime equals 1, p prime equals infinity is Hausdorff-Young, but we need some restrictions. Okay, we can look at the dth power, just like in the Drury method. And this sort of looks like a Fourier transform, I guess. This product of the a's is a little bit weird, but we can write an operator t that looks similar to before. And we get bounds on t. That will give us bounds eventually on m star and thus on m, just like in the Drury case. Okay, so what Drury did was break up into offspring curves and get an estimate that looks sort of like this. For us, it's going to be a little tricky because if you look at TG, this first equality, I'm writing the operator t in terms of t's and h's and offspring curves. And it's a little bit complicated, but we use Minkowski's inequality for integrals to bring the LP prime norm inside, and the h, we'll just put that on the outside. And each of these operators inside we'll call SH. We'd like to use the induction hypothesis on. That's what Drury did, but it'll be a little bit weird in this case, a little bit tricky. So here's our operator that we'd like to do the induction hypothesis on. We'll actually need the adjoint of this, so these products of Fourier transforms turns into a convolution, and this integral itself turns into a convolution of these operators a with f hat. And what I said long ago was that convolutions of these a's with something is like doing a maximal operator. So we have d many convolutions with a's, so we get a d-fold composition of maximal operators. Okay, and we use the induction hypothesis, we get our bounds, and we're happy, right? Wrong. Okay, so here is our inequality that we have. Induction hypothesis says something like this: MR f hat is bounded by f in LP, and there's a d up top here. There isn't a d over here, so we can't do the induction hypothesis. The induction hypothesis only has one maximal operator. So we have to go back to the beginning. We have to do everything all over again, prove the theorem for arbitrary compositions of maximal operators. And this is going to make it much trickier. All of the same ideas work, just it gets messy. The notation is horrible, but it does go through. And we do an L2 bound. There's some problems there, but I'm running short on time, so I'm going to skip through that. You can do some interpolation and get the same, end the proof in the same way as Drury. Some questions that I have. There was that gap between r equals p prime over d and r equals p prime that is unanswered right now. There's also these results, especially recently, we've been using the Drury method to do more general curves to take care of Fourier restriction on many different types of curves in RD. And there's this question of, can you extend maximal restriction theorems in the same way? And then, of course, you can look at other operators, other maximal operators, and ask, are there theorems there, and are there applications of those operators? The R maximal ones are nice because bigger values of R give you stronger convergence of averages. So I'd be interested if other maximal operators give you any nice statements about F, maybe in a pointwise sense or something else. That's all I have for you today. Sorry for going over time.